The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so we're going to continue to look at stuff in space. So we've been working with triple integrals and seeing how to set them up in all sorts of coordinate systems. And the next topic we'll be looking at are vector fields in space. And so in particular, we'll be learning about flux and work. So just for a change, we'll be starting with flux first, and we'll do work actually after Thanksgiving. So just to remind you, well, a vector field in space is just the same thing as in the plane. At every point you have a vector field. At every point you have a vector, and the components of this vector depend on the coordinates x, y, and z. Okay, so let's say the components might be P, Q, R, or your favorite three letters, where each of these things is a function of the coordinates x, y, z. And so you've seen that in the plane it's already pretty hard to draw a vector field. So usually in space we won't really try too hard, okay? But it's still useful to try to have a general idea for what the vectors in there are doing, whether they're all going in the same direction, whether they may be all vertical or horizontal, pointing away from the origin towards it, things like that. But we won't, generally speaking, we won't really bother with trying to draw a picture because that's going to be quite hard. Just to give you examples, well, the same kinds of examples as in the plane, you can think of force fields. So, for example, the gravitational attraction of a solid mass at the origin on a mass m at, let's call this mass big M, at a point x, y, z, that would be given by a vector field that points towards the origin and whose magnitude is inversely proportional to the square of the distance from the origin. Okay, so such a field would be directed towards the origin, and its magnitude would be of the order of a constant over rho squared, where rho is the distance from the origin. Okay, so the picture, if I really wanted to draw a picture, would be everywhere it's a field that points towards the origin, and if I'm further away, then it gets smaller. And of course, I'm not going to try to draw all these vectors in there. Okay, so if I wanted to give a formula for that, so a formula for that might be something of a form minus c times xyz over rho cubed. Let's see. Well, the direction of this vector, so this vector is proportional to negative xyz. Xyz is the vector that goes from the origin to your point. The negative goes towards the origin. Then the magnitude of this guy, well, magnitude of x, y, z is just distance from the origin. It's rho. So the magnitude of this thing is 1 over rho squared times some constant factor. Okay, so that would be an example of a vector field that comes up in physics. Well, other examples would be electric fields. Actually, if you look at the electric field generated by a charged particle at the origin, it's given by exactly the same kind of formula. And there's magnetic fields. And so on. Another example comes from velocity fields. So if you have a fluid flow, for example, if you want to study wind patterns in the atmosphere, well, wind most of the time is kind of horizontal, but maybe it depends on the altitude. You know that at high altitude you have jet streams. The wind velocity is not the same at all altitudes. And just to give you more examples, well, in math, we've seen that the gradient of a function of three variables gives you a vector field. If you have a function u of x, y, z, then its gradient field has just components u sub x, u sub y, and u sub z. And of course, the cases are not mutually exclusive. Right? For example, the electric field or gravitational field are given by the gradient of the gravitational or electric potential. So, these are not like different cases. There's overlap. Okay, so anyway, hopefully you're kind of convinced that you should learn about vector fields. What are we going to do with them? Well, let's start with flux. So remember, not so long ago, we've looked at flux of a two-dimensional vector field through a curve. So we had a curve in the plane, and we had a vector field and we looked at the component of a vector field in the direction that was normal to the curve. So we formed the flux integral that was a line integral f dot n ds, and that measured how much the vector field was going across the curve. So if you were thinking of a velocity field, that would measure how much fluid is passing through the curve in unit time. Okay, now let's say that we're in space. Well, we can't really think of flux as a line integral, because if you have, a curve in space, and say that you have wind or something like that, you can't really ask how much air is flowing through the curve. See, to have a flow through something, you need actually a surface. If you have a net, maybe, then you can ask how much stuff is passing through that surface. So there's going to be a big difference here. In the three-dimensional case, flux will be measured through a surface. And so it will be actually a surface integral, not a line integral anymore. So that means we'll be integrating, we'll be summing over all the pieces of a surface in space. Okay, because a surface is a two-dimensional object that will end up being a double integral. But of course, we'll have to set it up properly because the surface sits in space. So probably we'll have x, y, and z to deal with at the same time. And we'll have to somehow get rid of one variable so that we can set up and evaluate a double integral. So conceptually, it's very similar to line integrals. Just, in a line integral in the plane, you had two variables that you reduced to one by figuring out what the curve is. And here you'll have three variables that you will reduce to two by figuring out what the surface is. Okay, so let me give you the definition of flux in 3D. So let's say that we have a vector field. And S, a surface in space. So let me draw some kind of picture. I have my surface, and I have my vector field F. Well, at every point, it changes with a point. Well, I want to figure out how much my vector field is going across that surface. So that means actually I want to figure out the normal component of my vector field. Okay, so I will use, as in the plane case, the unit normal vector to S. Okay, so, I take my point on the surface, and I build a unit vector that's standing on it perpendicularly. Now, well, we have to decide actually which way it's standing. Right? We can build our normal vector to go this way or to go the other way around. There's two choices. Basically, whenever you want to set up a flux integral, you have to decide, you have to choose one side of the surface. And you will count positively what flows towards that side, negatively what flows towards the other side. So there's two choices for n. We need to choose a side of the surface. So in the case of curves, see, actually, we made that choice by deciding that because we were going along some direction along the curve, we could choose one side by saying, let's rotate clockwise from the tangent vector. And in a way, what we were doing it was a recipe to choose for us one of the two sides. So here we don't have a notion of orienting the surface other than by precisely choosing one of the two possible normal vectors. So in fact, this is called choosing an orientation of the surface. When you're saying that you're orienting the surface, that really means you're deciding which side is which. Okay, so that's called an orientation. Now, there's no set convention that will work forever, but the usual traditional settings would be to take your normal vector pointing maybe out of a solid region, because then you'll be looking at flux that's coming out of that region of space. Or if you have a surface that's not like closed or anything, but maybe you will want the flux going up through the region. Or there's various conventions. So, concretely on problems, it will either say which choice you have to make, or you get to choose which one you want to make. And of course, if you choose the other one, then the sign becomes the opposite. So now, once we've made a choice, then we can define the flux integral. It will just be the double integral over the surface of f dot n ds. So now I'm using a big ds that stands for the surface area element on this surface. I'm using ds rather than dA because I still want to think of dA as maybe the area in one of the coordinate planes, like the one we had in double integrals. You'll see later where this comes in. But conceptually, it's very similar. Okay, so concretely what this means is, I cut my surface into little pieces. Each of them has area delta S, and for each piece, I take my vector field, I take my normal vector, I dot them, and I multiply by this surface area, and I sum all these things together. That's what the double integral means. So in particular, an easy case where you can get away without computing anything is, of course, if your vector field is tangent to the surface. Because then you know that there's no flux. I mean, flux is going to be 0 because nothing passes through the surface. Otherwise, well, we have to figure out how to compute these things. So that's what we're going to learn now. Well, maybe I should box this formula. I've noticed that some of you seem to like it when I box the important formula. So OK. By the way, a piece of notation before I move on. So sometimes you'll also see the notation vector ds. What is vector ds? Vector ds is this guy nds put together. Okay, so vector ds is a vector which points perpendicular to the surface and whose length corresponds to the surface element. And the reason for having this shortcut notation, well, it's not only laziness, like saving one n, but it's because this guy is very often easier to compute than it is to set up n and ds separately. Actually, if you remember in the plane, we've seen that vector n little ds can be written directly as dy comma negative dx. That was easier than finding n and ds separately. And here the same is going to be true in many cases. OK. So first, sorry, any questions before we do examples? No? OK, let's do examples. So the first example for today, we're going to look at the flux of the vector field xi plus yj plus zk through the sphere of radius a centered at the origin. Okay, so what does the picture look like? So we have a sphere of radius a. I have my vector field. Well, x comma y comma z, see, that's a vector field that's equal to the vector from the origin to the point where I am. So it's pointing radially away from the origin. Okay. So my vector field is really sticking out everywhere away from the origin. Now I have to find the normal vector to the sphere if I want to set up double integral over the sphere of f dot vector ds, or if you want, f dot n ds. So what does the normal vector to the sphere look like? Well, depends, of course, whether I choose it pointing out or in. Let's say I'm choosing it pointing out, then it will be sticking straight out of the sphere as well. So hopefully you can see that if I take the normal vector to the sphere, it's actually pointing radially out away from the origin. So in fact, our vector field and our normal vector are parallel to each other. Okay, let's think a bit more about what the normal vector looks like. So I say it's sticking straight out. It's proportional to this vector field. So maybe I should start by writing x, y, z, because that's the vector that goes from the origin to my point, so it points radially away from the origin. Now there's a small problem with that. It's not a unit vector. So what is its length? Well, its length is square root of x squared plus y squared plus z squared. But if I'm on the sphere, then that length is just equal to a, because distance from the origin is a. So in fact, I get my normal vector by scaling this guy down by a factor of a. Okay? And let me write down, just in case you're still unsure, this is unit because square root of x squared plus y squared plus z squared is equal to a on the sphere. Okay. Any questions about this? No? Looks okay? I see a lot of blank faces. That physics test must have been hard. Yes? I could have put rho, but I want to emphasize the fact that here it's going to be a constant. See, I mean, rho has this connotation of being a variable that I will need to then maybe integrate over or do something with. And yes, it would be correct to put rho, but I really want to put, then later I will want to replace it by its actual value, which is a number, then the number is A. It's not going to actually change from point to point. For example, if this was the unit sphere, then I would just put, x, y, z. I wouldn't divide by anything. Okay, so now let's figure out f dot n. Let's do things one at a time. Well, f and n are parallel to each other. So f dot n, the normal component of f, is actually equal to the length of f. Well, times the length of n if you want, but that's going to be 1, since f and n are parallel to each other. And what's the magnitude of f if I'm on the sphere? Well, the magnitude of f in general is square root of x squared plus y squared plus z squared. On the sphere, it's going to be a. Okay, the other way to do it, if you don't want to think geometrically like that, is to just do the dot product x, y, z dotted with x over a, y over a, z over a. You will get x squared plus y squared plus z squared divided by a. That will simplify to a, because we're on the sphere. So see, we're already actually using here the relation between x, y, and z. We are not letting x, y, and z be completely arbitrary. But the slogan is everything happens on the surface where we're doing the integral. We are not looking at anything inside or outside. We're just on the surface. So now, what do I do with that? Well, I've turned my integral into the double integral of a ds. And a is just a constant. So I'm very lucky here. I can just say, well, this will be a times the double integral of ds. And of course, someday I'll have to learn how to tackle that beast. But for now, I don't actually need to, because the double integral of ds just means I'm summing the area of each little piece of the sphere. I'm just going to get the total area of the sphere, which I know to be 4 pi a squared. Okay, so this guy here is going to be the area of S. So I know that to be 4 pi a squared. So I will get 4 pi a cubed. Okay, so that one was relatively painless. That was too easy. So let's do a second example with the same sphere, but now my vector field is going to be just z times k. Well, let me give it a different name. Let me call it h instead of f or something like that, just so that it's not called f anymore. Okay, well, the initial part of the setup is still the same. The normal vector is still the same. What changes is, of course, my vector field is no longer sticking straight out, so I can't use this easy geometric argument. It looks like I will have to compute f dot n and then figure out how to integrate that with ds. So let's do that. So we still have that n is x, y, z divided by a. So that tells us that h dot n will be, well, 0, 0, z dot x, y, z over a. Looks like I will be left with z squared over a. Sorry. So h dot n is z squared over a. So the double integral for flux now becomes double integral on the sphere of z squared over a ds. Well, we can take out the 1 over a, that's fine, but looks like we'll have actually to integrate z squared on the surface of the sphere. So how do we do that? Well, we have to figure out what is ds in terms of our favorite set of two variables that we'll use to integrate. Now, what's the best way to figure out where you are on the sphere? Well, you could try to use maybe theta and z. If you know how high you are and where you are around, in principle, you know where you are on the sphere. But since then, since cylindrical coordinates, we've actually learned about something much more interesting, namely spherical coordinates. It looks like longitude, latitude is the way to go when trying to figure out where you are on a sphere. So we're going to use phi and theta. And of course, we have to figure out how to express ds in terms of d phi and d theta. Well, if you were paying really, really close attention last time, then you'll notice that we've actually already done that. Okay? So last time, we've seen that if I have a sphere of radius a, and I take a little piece of it that corresponds to small changes in phi and theta, then we said that, well, we argued that this side here, the one that's going east-west, was a piece of a circle of radius. So this east-west circle has a radius a sine phi, because that's r. So that side is a sine phi delta theta. And the side that goes north-south is a piece of a circle of radius a, corresponding to angle delta phi, so it's a delta phi. And so just to get to the answer, we got ds equals a squared sine phi d theta. Okay, so when we set up a surface integral on the surface of a sphere, most likely we'll be using phi and theta as our two variables of integration, and ds will become this. Now, it's okay to think of them as spherical coordinates, but I'd like to encourage you not to think of them as spherical coordinates. Spherical coordinates are a way of describing points in space in terms of three variables. Here, it's more like we're parametrizing the sphere. We're finding a parametric equation for the sphere using two variables, phi and theta, which happen to be part of the spherical coordinate system. But see, there's no rho involved in here. I'm not using any rho ever, and I'm not going to in this calculation. I have two variables, phi and theta. That's it. Okay, it's basically in the same way as when you parameterize a line integral on a circle, we use theta as the parameter variable, and we never think about r. Okay, so that being said, well, we're going to use phi and theta. We know what ds is. We still need to figure out what z is. Well, so there we want to think a tiny bit about spherical coordinates again, and we'll know that z, well, is just a cosine phi. Okay? In case you don't quite see it, let me draw a small diagram. You know that phi is the angle down from the positive z-axis. This distance is a, so this distance here is a cosine phi. Okay? So now I have everything I need to compute my double integral. Z squared over a ds will become a double integral of, so z squared becomes a squared cosine square phi, over a, times ds becomes a squared sine phi d phi d theta. Now I need to set up bounds. Well, what are the bounds? Phi goes all the way from 0 to pi, because we go all the way from the North Pole to the South Pole. And theta goes from 0 to 2 pi. Okay. And of course, I can get rid of some a's in there and take them out. Okay. So let's look actually at what number we get. So first of all, we can take out all those a's. We get an a cubed. Okay? Second, so in the inner integral, we are integrating cosine square phi sine phi d phi. I claim that integrates to cosine cubed up to some factor, and that factor should be negative 1/3. Okay? If you look at cosine cube phi and you take its derivative, you'll get that guy with a negative 3 in front between 0 and pi. And while integrating over theta, we'll just multiply things by 2 pi. So let me add a 2 pi in front. Okay, and now if I evaluate this guy between 0 and pi, well, at pi, cosine cube is negative 1. At 0, it's 1. I will get actually 2/3 out of this. So I end up with 4/3 pi a cubed. Okay, sorry, I didn't write very much, but trying to save Blackboard space. Yes. Yes, that's a very natural question. That looks a lot like somebody we know, like the volume of a sphere, and ultimately it will be. Wait until next class when we talk about the divergence theorem. Okay. So, yeah, I mean, the question was, is this related to the volume of a sphere? And ultimately it is. But for now, it's just, some coincidence. Yes?
Is there a way to do it like what we did before, like mdy plus mdx?
So so the question is there a way to do it mdx plus ndy plus stuff like that? The answer is unfortunately no, because it's not a line integral. It's a surface integral. So we need to have two variables in there. So in a way, you'd end up with things like, some dx, dy's maybe, and so on. I mean, it's not practical to do it directly that way, because you'd have then to compute Jacobians to switch from dx, dy to something else. So we are going to see various ways of computing it. Unfortunately, it's not quite as simple as with line integrals. But it's not much harder. It's the same spirit. We just use two variables, and we set up everything in terms of these two variables. Okay. Any other questions? No? Okay. No. Okay. By the way, just some food for thought. No, never mind. Okay. So, conclusion of looking at these two examples is that sometimes we can use geometry. In the first example, we didn't actually have to compute an integral, but most of the time we need to learn how to set up double integrals. So use geometry, or you need to set up the double integral over the surface. And so we're going to learn how to do that in general. So as I said, we need to have two parameters on the surface and express everything in terms of these. So let's look at various examples. So we're going to see, various situations where we can do things. Well, let's start with an easy one. Let's call that number 0, actually. Say that my surface S is a horizontal plane. So say z equals a. Okay? So when I say a horizontal plane, it doesn't have to be the entire horizontal plane. You know, it could be a small piece of it. It could even be, to trick you, maybe an ellipse in there or a triangle in there or something like that. What you have to recognize is my surface, it's a piece of just a flat plane. So I should not worry too much about what part of the plane it is. Well, it will become important when I set up bounds for integration. But when it comes to looking for the normal vector, I can rest assured that the normal vector to a horizontal plane is just vertical. Okay, so it's going to be either k or negative k, depending on whether I've chosen to orient it pointing up or down. And which one I choose might depend on what I'm going to try to do. Okay, so the normal vector is just sticking straight up or straight down. Now, what about ds? Well, it's going to be just the area element in a horizontal plane. Just looks like it should be dx dy. I mean, if I'm moving in a horizontal plane, to know where I am, I should know x and y. Okay, so ds will be dx dy. So if I play the game that way, I have my vector field f. I do f dot n. That just gives me the z component, which might involve x, y, and z. X and y I'm very happy with. They will stay as my variables. Whenever I see z, well, I want to get rid of it, but that's easy because z is just equal to a. So I just plug that value, and I'm left with only x and y, and I'm integrating that dx dy. So it's actually ending up being just a usual double integral in xy coordinates. And of course, once it's set up, anything is fair game. I might want to switch to polar coordinates or something like that. Or I can set it up dx dy or dy dx. All the usual stuff applies. Okay, but for the initial setup, we are just going to use these and express everything in terms of x and y. Actually, a small variation on that. Well, let's say that we take vertical planes that are parallel to, say, maybe the blackboard plane. So parallel to the YZ plane. So that might be something like x equals some constant. Well, what would I do then? It would be pretty much the same. The normal vector to this guy would be sticking straight out towards me or away from me. Let's say I'm having it come to the front. Well, so the normal vector would be plus minus I. And the variables that I would be using to find out my position on this guy would be y and z. So, and in terms of those, the surface element is just dy dz. Similarly for planes parallel to the xz plane using, well, I'm sure you can figure that one out. Okay. So, these are somehow the easiest ones because those we already know how to compute without too much trouble. What if it's a more complicated plane? Well, we'll come back to that next time. Let's explore some other situations first. Okay, number one on the list, after number 0. Well, let's say that I gave you a sphere of radius a centered at the origin, or maybe just a half of that sphere or some portion of it. Well, we've already seen how to do things. Namely, we'll be saying the normal vector is x, y, z over a. Well, plus or minus, depending on whether we want it pointing in or out. And ds will be a squared sine phi, d phi, d theta. So in fact, we will express everything in terms of phi and theta. So if I wanted to, I could tell you what are the formulas for x, y, z in terms of phi and theta. You know them. But it's actually better to wait a little bit. It's better to do f dot n, because f is also going to have a bunch of x's, y's, and z's. And if there's any kind of symmetry to the problem, then you might end up with things like x squared plus y squared plus z squared, or things that have more symmetry, that are easier to express in terms of phi and theta. So the advice would be, first do the dot product with f, and then see what you get, and then turn it into phi and theta. Okay, so that's one we've seen. Let's say that I have, so it's a close cousin. Let's say I have a cylinder of radius a centered on the z-axis. Okay, so what does that look like? And when I say a cylinder, it could be a piece of cylinder. So first of all, what does the normal vector to a cylinder look like? Well, it's sticking straight out, but sticking straight out in a slightly different way from what happens with a sphere. See, the sides of a cylinder are vertical. So if you imagine, you have this big cylindrical pipe in front of you, hopefully you can see that the normal vector is going to always be horizontal. It's sticking straight out in the horizontal directions. It doesn't have any z component. So the normal vector, I claim the normal vector for the cylinder. See, if you have a point here at x, y, z, well, it would be pointing straight out away from the central axis. So my normal vector, well, if I'm taking it to point outwards, will be going straight away from the central axis. That means, if I look at it from above, maybe it's easiest if I look at it from above, look at x, y. So then my cylinder looks like a circle, and the normal vector just points straight out. See, it's the same situation as when we had a circle in the 2D case. The normal vector for that is just going to be x, y, and 0 in the z component. Well, plus minus, depending on whether you want it sticking in or out. It's fixed. Okay. So we said on our cylinder, normal vector is plus minus x, y, 0 over a. What about the surface element? So before we ask that, actually, maybe we should first figure out what coordinates are we going to use to locate ourselves in a cylinder. Well, yes, we probably want to use part of the cylindrical coordinates, except for, well, we don't want r because r doesn't change. It's not a variable here. Indeed, you probably want to use z to tell how high you are and theta to tell you where you are around. So ds should be in terms of dz d theta. Now, what's the constant? Well, let's look at a small piece of our cylinder corresponding to a small angle delta theta and a small height delta z. Well, the height, as I said, is going to be delta z. What about the width? It's going to be a piece of a circle of radius a corresponding to the angle delta theta. So this side will be a delta theta. So delta s is a delta theta delta z. So ds is just a dz d theta or d theta dz. Doesn't matter which way you do it. Okay? And so when we set up the flux integral, we'll take first the dot product of f with this normal vector. Then we'll stick in this ds. And then, of course, we'll get rid of any x and y's that are left by expressing them in terms of theta. Maybe x becomes a cosine theta, y becomes a sine theta. Okay, so these various formulas, you should try to remember them because they're really useful. So for the sphere, for the cylinder, hopefully those for the planes you kind of know already, intuitively. Okay, what about more general surfaces? Not everything in life is made out of cylinders and spheres. I mean, it's a good try, but so let's look at a more general kind of surface. Let's say I give you the graph of a function z equals f of xy. So this guy is nothing to do with the integrand. It's not what we're integrating. We're just integrating a vector field that has nothing to do with that. This is how I want to describe the surface on which I will be integrating. Okay, so my surface is given by z is a function of xy. Well, I would need to tell you what n is and what ds is. And that's going to be slightly annoying. I mean, actually, I don't want to tell them separately because you'll see they're pretty hard. So instead, I'm going to tell you that in this case, well, let's see, what variables do we want? So I'm going to tell you a formula for n ds. Okay? But so what variables do we want to express this in terms of? Well, most likely x and y, because we know how to express z in terms of x and y. So, you know, this is an invitation to get rid of any z that might be left and set everything up, set everything up in terms of dx, dy. So the formula that we're going to see, I think we're going to see the details of why it works tomorrow, is that you can take negative partial f partial x, negative partial f partial y, and 1 dx dy. Plus minus, depending on which way you want it to go. So if you really want to know what is ds, well, ds is the magnitude of this vector times dx dy. So see, there will be a square root and some squares and some stuff. What's the normal vector? Well, you take this vector and you scale it down to unit length. Okay, so just to emphasize it, this guy here is not n, and this guy here is not ds. Okay, each of them is more complicated than that, but the combination somehow simplifies nicely. And that's good news for us. So now, concretely, the one way you can think about it is this tells you how to reduce things to an integral over x and y. And of course, you will have to figure out what are the bounds on x and y. So that means you'll need to know what does the shadow of your surface look like in the xy plane. So then to set up bounds, on whatever you will get dx dy, well, of course, you can switch to dy dx or anything you like, but you will need to look at the shadow of S in the xy plane. But only do that after you've gotten rid of all the z. Right? When you no longer have z, then you can figure out what are the bounds for x and y. Okay. Any questions about that? Yes? Oh, for the cylinder. Okay. So let me re-explain quickly how I got the normal vector for the cylinder. So if you know what a cylinder looks like, you probably can see that the normal vector takes straight out of it horizontally. So that means the z component of n is going to be 0. Okay? And then the xy components you get by looking at it from above. Wait. One last thing I want to say. Okay, so what about the geometric interpretation and how to prove it? Well, if your vector field f is a velocity field, then the flux is the amount of matter that crosses the surface that passes through S per unit time. And the way that you would prove it would be similar to the picture that I drew when we did it in the plane. Namely, you would consider a small element of the surface, delta S, and you would try to figure out what's the stuff that flows through it in a second. Well, it's the stuff that lives in a small box whose sides, well, whose base is that piece of surface, and whose other side is given by the vector field. And then the volume of that is given by base times height, and the height is f dot n. Okay, so it's the same argument as what we saw in the plane. Okay, so next time we'll see more formulas. We'll first see how to prove this, more ways to do it, more examples, and then we'll get to the divergence theorem.